So we've got two presenters tonight. We've got Mike and Doug. They're longtime Raleigh Astronomy Club members, and both of them are NASA JPL Solar System Ambassadors. And I was asked to keep the bio short. So guys, are you ready? All right, take it away.
All right, thank you. So Doug, you entertain while I get the slideshow going.
All right. You like that, eh? Yeah, that was over from my old Wallville days, you know. As you can tell, I didn't quit my day job. So yeah, Mike and I have been longtime cohorts in doing presentations, and we've also had a long discussion on life that existing outside of our own Earth. And so we've over the past few years, we've developed presentations on life elsewhere, the probability of it being there, some of the things that NASA is looking at right now. So Mike has recently kind of taken a lot of that discussion, and I want to say he's coalesced it into more of a summary of some of the things that we've been talking about over the last 2 or 3 years. And so it'll be Where Are All the Aliens? Looks like you're about ready to rock and roll, Mike. So I'm going to hand it right over to Mike. Thank you. Mike.
All right, so anybody recognize this guy? All right, this is not that talk, thankfully. All right, so we're not going to go in there, but yeah, and I think you're up.
Oh, I am. All right. All right. So what is life? And this is one of the things that I think puzzles everyone. We all think we know what it is, but what are some of the things that actually define life? I actually used to work for a company that put quite a bit of money and research into trying to kind of break that code of life, try to actually create life, artificial life. They weren't very successful, but anyway, as we were going on with the talk and everything, I think Mike and I kind of sat down and kind of decided, okay, what are some of the parameters that we look at that actually define life? So let's go to the first one. First of all, there's no one definition. So what you hear from Mike and I tonight, these are just things that we've looked at, we've read about, but there's not really one all-encompassing definition. But there are a few things that we can look at that actually kind of tell us what life might be like. So first one is order and structure. So something that's living has got to have order and structure. It's got to provide some type of function, and it has to be made up of body parts like cells, roots, bones, DNA. And so that basically allow that organism to function.
All right, and next, whatever organism or thing that we're looking at has got to be able to process information. So it's gonna respond to external stimuli. So in other words, you put it next to something really, really hot, it will move away, or it will screech, or it will do something. But yeah, it basically responds to external stimuli.
Then next, growth. So it's got to be able to increase in size and the size of its body parts, and not just accumulate or amass matter. So, and more importantly, it's got to be proportional to its size. In other words, you don't have like one big, massive like arm or appendage out here, and then tiny little scrunched up little body over here. There is an order, a structure, and there is a proportion to its growth as it's growing.
Yeah, so just because you roll a snowball bigger doesn't mean it's alive. Homeostasis. So we're challenging your SAT skills here, and remember this definition, but it has to maintain and regulate its own internal conditions despite whatever's going on outside. Some people might say, oh, well, then cold-blooded animals aren't that way. That's not correct. Cold-blooded doesn't mean they actually have cold. It's just the amount of energy that they're consuming actually goes down, so they become slower or hibernate or things like that. So again, trying to maintain your internal conditions despite whatever the outside throws at you.
I don't know about you, but I have trouble maintaining my own internal conditions on a regular basis. All right, let's see the next one. Okay, being able to metabolize. That means we're able to capture, consume, we're able to get food, we're able to get energy in some way and convert that energy either into heat, sugars, complex sugars, and for that process of growth and homeostasis that we talked about just a little bit earlier.
Yes, we're kind of building on each one of these things, but an organism also needs to be able to reproduce, and it needs to reproduce new organisms of its kind. So not like a tree isn't exactly, yeah, it's not like a tree is going to make a frog.
Exactly. Okay, everything after its own kind. All right, and so then also adaptation. So we know that we've had examples on our own planet where there have been animals, there have been life forms that have not been able to adapt, and what's happened to them? Well, they've gone extinct and everything. So really, we want to talk about life that's able to thrive. You've got to talk about adaptation. It's got to be able to adapt to its surroundings, and it has to be able to evolve, change with respect to those stimuli that Mike talked about a little bit earlier.
Yep. Okay, come on, jump. Okay, so where are some of the really strange places where we have found life? We used to think that life was very fragile, but we know differently. And has anyone heard of extremophiles in the room here? Raise your hand. Okay. So these little buggers are quite impressive. And this is an example of one of these tardigrade or extremophiles. Anyone a Doctor Who fan? Okay, in the room, nobody's a Doctor Who fan. Okay. Hopefully online in the Zoom meeting, we've got some, but there was so these little tiny creatures, they're super, super small, but there was an experiment called TARDIS, so tardigrade in space. And these little guys survived 12 days in the complete vacuum of space with radiation, you name it. And basically, when they brought them back in, hydrated them, absolutely no problem at all with their survival or reproduction, and just absolutely amazing. Then we've got things like radioactive waste. I'm not even going to try to pronounce this thing, but there is bacteria that can live inside a nuclear reactor. In fact, they thrive on this sort of radiation, which, like, what in the world would cause something to evolve to the point where it could withstand this? And in one particular experiment, they actually survived 3 years outside of the ISS, sorry. And that's basically the amount of radiation they're getting that way, not including the fact that there's no air, no water, no nothing. That's 200 times what they can, what they would receive here on Earth. And when you think about just in general, the fact that we find life down in the very depths of the oceans under crushing pressure near basically boiling water, and we've got life that's thriving, and it's not just little microscopic life. You've got some of these tube worms and things that can be feet long, but there is absolutely life down underneath. I know, just miles of ocean. So again, we just find life here, and it's like, how would it evolve that way? And I'm not going to go into each one of these here, but there are these other extremophiles. If someone wants, the papers are up there. But the two that really impress me are, there's one bacteria that can withstand 400,000 times its own weight. So in other words, 400,000 G's. Again, why? Another one of these little guys can survive impacts that, extreme shock, extreme deceleration. And if you look at what those speeds are, that's kind of like an asteroid impact. So again, why are these things that, just robust? So life is definitely not as fragile and as simple as we've thought.
All right, so we're going to get into some of the spacecraft and probes that NASA has sent out with respect to finding life. Now, really, the only probe that we actually really sent out that really had the experiments for detecting biologics were this Viking spacecraft back in the mid 1970s through early 80s. And so these spacecraft were actually designed, they actually had experiments to find biologics. Now you say, well, what about all the current probes that we have out there, all the robots roving and everything? They actually don't have biologic experiments on them. What they do have is they are looking for building blocks of life. So they're going to be looking for water. They're looking for evidences of salts and other organic, I should say, organic molecules. But specifically, there were experiments on the Viking spacecraft for detecting biologics. And lo and behold, both spacecraft did return positive results for biologics. However, unfortunately, the experiments were flawed. And so they really came under scrutiny. One of the things is that there's a mass spectrum, there was a chromatography package and a mass spectrometer on there. And of course, the chromatography package is really there to kind of separate the individual atoms from one another, kind of break up those organic molecules into atoms so we can see what's there. And the mass spectrometer then analyzes what those specific atoms are. What happened is that as they were analyzing the soils and stuff that they were picking up, they realized that, well, wait a minute, the moon actually has more carbon and more more organic molecules than actually has 4 times that of Mars. So when they got a positive result, they're saying, well, how can we have a positive result when we virtually have no organic compounds on Mars? The other thing too was that the actual experiment they had actually was destructive for organic material. So they couldn't actually detect any organics after the experiment was run. So there wasn't anything to go back to. Plus they had other problems with the way that the controls had been designed. So unfortunately, they have now pretty much discounted the results there. And we certainly haven't found anything else on Mars. We do definitely see that there's water there, but unfortunately, we just can't, they're just not counting on this experiment for now.
Yeah, I think it's a conspiracy theory. They found it and they just don't want to let it out. No, I am kidding. I'm kidding. Exactly. All right. Let's see why it's not moving forward. Okay, so Doug mentioned the current rovers, and without going into a lot of detail about what what their missions were, but Spirit and Opportunity proved liquid water had flowed once on Mars. There was absolutely irrefutable proof to see how those rocks were molded. Curiosity, currently exploring the surface of Mars, basically provided evidence that freshwater lakes actually persisted. So meaning they just weren't there for a little bit and then they went away, but persisted for millions and millions of years around Gale Crater. And they contained the key elements for life. Now, Perseverance, that's the newest one, that's going to also search for ancient signs of microbial life. And if you think about, Doug mentioned the experiments, very hard to basically run an experiment. How many, 60 million miles away potentially on that, with at best maybe 10 minutes of communication time. So you have to write all the code up in front and it has to be autonomous. And it's just really hard to do experiments. So this is actually going to, Perseverance will take core samples and eventually package them together and cache them for an eventual return mission. So hopefully, that will help us. And again, as Doug mentioned, we, in the process, those samples were destroyed. At least in this case, we'll have enough samples that we can do the right sort of experiments.
All right, and so what we're doing now also with Mars is we actually have 2 orbiters. We have the MRO, which is the Mars Reconnaissance Orbiter. The Mars Reconnaissance Orbiter, of course, is making detailed maps of Mars, but it's also trying to understand the climate and how climate has changed on Mars. We have another orbiter, and by the way, these are all still orbiting the planet. We have MAVEN, which is basically the Mars Atmosphere and Volatile Emission mission. And what that's doing is that it's actually kind of trying to understand how Mars lost that water. The water is so important to life. It's so important to all the chemical reactions that happen, not only in our bodies, but in the bodies of other organisms. And then just what happened to it? How did it, basically how did the atmosphere become rarefied, and how did it sublimate into space? And where is it? Maybe it's under. So Maven and Mainly is mainly looking at that atmosphere and kind of trying to understand that how it's changed over time.
Yeah. So another place where we are actively searching for aliens, or will search for aliens, was during the Galileo mission. And maybe I'm stretching that a little bit, but we did, as part of that mission, discover that Europa had a subsurface ocean, and it's more liquid water than we have on the entire Earth is basically estimated to be in that subsurface ocean. So definitely a place to look.
Okay, and one of the other really cool and exotic places, of course, is the moon Titan that's orbiting around Saturn. We found an absolutely amazingly exotic environment on that moon, where we have almost a completely nitrogen atmosphere. It's a lot of ethane and methane in the atmosphere. Also, too, it rains ethane. And they have lakes of ethane on the planet. Ice is actually a different form of ice. It's ice 5, I believe it is. And so it is as hard as rock, but it's so exotic that you could literally have a completely different kind of life form on there. So we really do need to get some missions going. We do have one we'll talk about a little bit later, but just the environment is just so exotic there. It just begs for life to be there. Also over here, well, this is a little artist's rendition. We actually had Cassini fly through the volcanic ice jets over the moon in Cladis. And so this is kind of an artist's depiction of it moving through there. And Cassini was able to detect organic compounds in those water jets. So that's another really exciting place. It's also for our own habitable experience. That's a really exciting place that could possibly harbor human life if we were to put a base there. You've definitely got the heat, and you've got the water. You can generate rocket fuel. You can generate oxygen. It's a perfect place for putting an outpost. So that's some very interesting. There's some there's interesting data on Cassini, but on interest of time, we're going to move forward.
Yep. And so these are the missions that NASA is planning to go ahead and search or study conditions for possible life. So Europa Clipper is going to head out there. Fingers crossed. Launch date of 2024. I haven't seen anything that's negative. Yes, we won't have that debate. Exactly. But yeah, so, this is a really good candidate for, possible life. And again, NASA being burned on the Viking missions, there was a time where, absolutely under no circumstances could you say that a mission was going to search for life. So that still somewhat holds true. So this next mission to Europa is basically going to look for conditions suitable for life.
All right, here's the really cool one that's coming up, and that's called Dragonfly. And Dragonfly is slated to launch to the moon Titan. It's going to be nuclear powered. So just to let you know, we've already landed one nuclear power aircraft carrier on the surface of Mars. First country to do that, right? So we landed Ingenuity, which was able to fly off. And now we're going to land Dragonfly onto the surface of Titan. And it'll be nuclear powered because it's so cold on Titan. Any conventional batteries would just be depleted in just a matter of hours. So Dragonfly is going to fly around to different aspects of the Titan surface and be doing surveying there. And since we already have a proof of concept with Mars Ingenuity, we're now making another aerial vehicle to fly across the surface. So it will be really super interesting. We're going to learn a lot about Titan from this project. It's launching in 2027, so not far off.
Yeah, it's kind of interesting to think that, you know, all we know about Titan was pretty much from the Cassini mission and the Huygens probe, which I can't remember how long that lasted. 5 hours. Yeah. So that's all we've got. So now we're going to jump outside of our solar system and talk about exoplanets. If anyone's interested, I've found that this app, I know it's an iOS app. I do believe there's also a Google Play version, but great app and gives you all kinds of information as to exoplanets and finding them. And that's a little screenshot, but really interesting app. So when we actually graph what we've found so far, if we look at this particular graph on the vertical axis is basically we're talking about mass, how heavy that those planets are. And again, this is in terms of Jupiter masses. So you can imagine that Earth is quite tiny compared to Moon. Yeah. So exactly. So, and that little purple line is describing exactly that. Okay, that's where Earth is on the spectrum. So you can see the planets we have been finding, for the most part, are much bigger. Then on the basically the horizontal axis, that is the period. So that's basically the year. How many Earth days it takes for all these planets to actually go once around their host star. And so here's Earth right there. Now, most of the planets we have found are, you know, inside of that. So they're closer than our Earth is to the sun. And you can basically see when we look at the transit, so that's the green pieces. It's very difficult to find transits that are more than a year long, or even getting close to that, because you've got to watch it for so long. You know, if you think about anyone that was using that method to see how many planets we have around the sun, they'd be lucky if they could get Earth, because it's not just one time. You got to detect a pattern, so you got to detect it over years. Probably wouldn't detect Mars. Definitely not Jupiter or Saturn or anything out there. But that's where you get into radial velocity. So in other words, how much tug does a planet have on its host star? And that's everything that's in the kind of the red bucket. So those you can actually detect much better. Using that method, things that orbit their host star much further out. So, you know, again, we're still kind of in the infancy of finding exoplanets, but there's a graph, and this is as of October of 22, kind of like if we put in terms of Earth, what have we found so far?
And if you think back to Mike's slide there, his previous slide, you can see that we've actually begun to find some planets that are kind of in that Earth-like rotation, or sorry, the Earth-like orbiting period. So that's actually good news. Now this one looks a little complicated, but if you start, these big circles are going to be like Jupiter-sized planets. The little smaller is going to be Neptune size. Some are going to be somewhere between a super Earth and Earth. But of course, the ones we really like are these small dots, which are the ones that are about the size of Earth. And so these are planets that we're really kind of beginning to look at now. So that's what the symbols represent on this graph. When you look at what we see in terms of these shaded areas, we're talking really about habitable zone and greenhouse effect. So the greenhouse effect is very important, of course, to Earth, because with the greenhouse effect, that's, of course, the evaporation, the hydrology cycle that we have with rain, precipitation, and stuff like that. So we want to be able to find something that's in that zone. What we have here on the vertical part is, of course, information with respect to the stellar temperature. How hot is the star that's near that planet? And then on the bottom here, we have this kind of crazy thing called planetary flux. And that's actually the energy that's actually being radiated off of the planet as a result of the greenhouse effect. Now, how you begin to interpret this graph is when you look at this thing, Look over here at Venus. Venus is kind of hot. And that's because a lot of the solar radiation is actually kind of, it is being bounced off the planet, but the solar radiation that makes it into Venus actually creates an IR pump, which pumps the temperature very hot on that surface of that planet. And so that's a very hot planet. So if you look over here, these are very hot planets. Venus is just outside what we would think of as a habitable zone. That's not that we can't have life there, because as Mike just talked about with respect to extremophiles, there certainly could be something there. And so we have on my Venus talk, another plug for Venus. I talk a lot about the possibility for life and other things that are happening on Venus. But what we really want to begin looking at are those planets that are actually as somewhat Earth-like, but sitting out here in this habitable zone. And just to remind you guys, the habitable zone is really defined as the place that a planet on a planet where liquid water exists. So the planet's got to be at that right position away from its host star, where it's not too cold, it's not too hot. Some people call it the Goldilocks zone. Everything's just right for liquid water. And we know about Venus, all the water is boiled up into the upper atmosphere. It's actually in its upper atmosphere. Mars, the water has rarefied. It's basically been sublimated off the planet. And what water we do have is locked up in ice and in possibly subterranean tunnels. Earth, on the other hand, is kind of in that right place. Go ahead, Mike, go to the next one. And so we've actually discovered some newer planets, and Mike's going to actually show those in more detail on the next slide. But we do have some new planets that we've actually discovered that are possible for life-bearing plants, because they are in that habitable zone. They're in the place where we would begin looking for life.
Yep. So remember, you may not be able to see it here in the room, but this first one is called Tea Garden Star. And the other one is, if anyone is familiar with the closest star system to our own, Proxima Centauri b. So, all right. And then this little dotted line, remember, these are all the Trappist planets. And some of you may remember what those were, announced several years ago. But this is something that is put out by the, it's the planetary, now I can't remember the name. So, and these are artist, depictions of what they think it could be, but they're using something called a Earth Similarity Index. So obviously the Earth is 1-to-1 or 100% like Earth. Then you've got Mars at basically 0.64. Jupiter is quite low, so is Neptune. But these are all of the ones that we have found that are basically very close to what Earth looks like, or what we would imagine. So, when you start looking at these areas, there's that Tea Garden Star that we mentioned earlier. That's 12 light years away. And we've got quite a few other ones that are pretty darn close. Proxima Centauri b, 4 light years away. And there's a good chance that that might be someplace habitable. It's got a 0.87 habitability or similarity index. Now, other information suggests that it's probably tidally locked to its star. So if there's going to be anything habitable, it's basically going to be around that range that's close to sunrise and sunset, and obviously not in the middle or not in the, towards the dead of night, because that wouldn't change on the planet. And then we have all of the different Trappist planets. So they're 40 light years away, but 3 of them are actually in kind of what we might think would be the habitable zone, or at least similar to Earth. You figure even the last one, Trappist 1F, that's 0.58. Now compare that to Mars, 6.4. I mean, and we're looking for life on Mars. So again, there's a lot that is within reach, basically.
All right, so now that we're talking about all these planets, exoplanets that are possibly close to us, what would be the probability that we could literally begin to inhabit or visit all of these planets within a certain period of time? Well, if you look at our galaxy and you look at the possibility that maybe we could travel about 10% the speed of light, for those of you who remember the speed of light, 186,000 miles per second, 300,000 meters per second squared. You take just 10% of that, that means that we're going to be traveling somewhere around, 18,600 miles per second. If we could get a spacecraft, we don't have a spacecraft that can travel that fast yet, but if we could get to that point and begin with maybe taking robotic spacecraft that could actually have the capability to land on a planet, take stock of the resources, replicate itself, and then launch back off to another one. Then we could begin possibly, so look here, right here, we're talking about 500 years from our home planet to maybe 2 others, and we're talking about within our own galaxy. Then you basically got step 4, you're getting out maybe another, 3,500 years up to 5,000 years. Then in about maybe 3.75 million years, we could, or another race could, completely touch every planet, every habitable planet in the galaxy. So these are estimates, of course. Go ahead. You have a question? Not a bad question, and possibly interesting thought, So it is, because they actually, the one robotic ship might not be the same as the other one because due to missing resources. So, but yeah, that's a good point. Although, we'll save that discussion for later. All right, for maybe over dinner afterwards. But the whole point is that we literally could over roughly about 3.75 million years, we could actually inhabit the entire galaxy. Now we're talking about roughly 4.7 billion years, 13.7 billion years for our own universe in existence. So that means there's certainly been enough time for that to happen. Right, Mike?
Yeah, exactly. So, in 4 to 10 million years, any intelligent race out there should be able to send robots, and we should be able to see evidence of them, but we don't, or do we? So next we're going to talk about, well, what's the probability of extraterrestrial life? And if anyone's familiar or has heard the name Frank Drake, he basically put this hypothesis, put this equation together literally on the night before their very first meeting of SETI. And he's like, okay, what are we going to talk about? But in this case, it basically, we're trying to determine the number of communicating civilizations that should be in the Milky Way galaxy. And it's got a whole bunch of different components. They're all listed here. We're going to walk through a little exercise, and we're going to kind of take a poll of what everyone thinks that they are.
You're going to make me the roving mic? All right, everybody. All right, everybody. So Mike's going to put in your answers to the Drake equation. So this is going to be a real-time exercise here. All right. So, forget those answers.
All right.
You guys thought that you weren't going to use algebra when we got older. Now here's the chance.
All right. So how many stars? Okay.
What, Naveen? Oh.
Take you to a website that has it embedded. All right.
Everybody? All right, let's get going. All right.
All right. So that's so basically, how many? The first part is
how many stars in the galaxy We have the Milky Way. We have about what 100 million stars, something like that, between 100 million and 400 million. So in your in this, how many? Basically, this represents the number of new star forming star or places in the galaxy, million stars. So just I need from the audience, just somebody put your hand up. How many stars? All right, Annalise, how many? 400 billion. All right. Okay.
So now, what fraction of the stars actually have planets around them? Now, realize, before the 1990s, we knew of none. There were none. So when Star Wars came out and we had Tatooine and all these other places, yeah, that was just fantasy at that point.
All right. Put your hand up. All right.
I'm going to say 75%.
75%. All right. All right.
So now this is kind of a weird one. This is the basically we're asking for an average number of how many places, and we're not asking how many worlds there are on average or in the habitable zone. We're asking places because guess what? We can have moons around gas giants that are basically being tidally squeezed back and forth, creating their own heat, creating their own environment, and they're well outside the habitable zone. So again, this is an average here.
All right. So you guys give me that average? Anybody? Take somebody from over on this side. All right.
I'll go with 0.5%.
0.5%. All right. All right.
All right. So now we've got, all right, what is the fraction of these habitable areas where life actually evolves? So another way of asking this is we're asking you, how hardy is life? How well can it actually, make an inroad? So again, remember our extremophiles.
All right. All right. Back here. 10%. All right. Very good. Excellent.
So now we've got now we've got life. Life has started. It's microbial. It's small. Now, what percentage of those microbes and whatever actually evolve to intelligent life? I've heard that there might be intelligent life here on Earth. We're not exactly sure, but again, what's the percentage where microbial life can become evolved intelligent life?
All right. Get somebody over here. What percentage can become intelligent life?
5%.
Okay, Ty says 5%.
So the next part is, so now we have intelligent life that can communicate beyond. Now, by the way, we've only been able to do that for about 100 years, communicate beyond our own planet. So, and this is in essence a question of asking, are intelligent, advanced life forms, are they going to be very xenophobic and not want to explore and, kind of just hold up in their own little world? Or are they going to go out and they're going to explore and they're going to try and communicate?
All right. I'll take somebody from over here. Just like we're looking for the fraction that can actually communicate outside.
2%.
2%. Finally, all right.
So this really kind of divides the people into pessimists and optimists. So we have to basically create a variable for time, because obviously maybe something that was very intelligent and evolved 8 billion years ago within the Milky Way galaxy, is that planet still around? Or is that civilization still around? Who knows? But we've got to try and put a time component. So this is about how many years does a civilization, thrive once it's become a communicating civilization. So, and again, think of Earth. We've only been able to communicate for about 100 years. So, are we an average possible, set of civilizations? And how long is the Earth going to survive? Or better yet, how long are human beings going to survive without blowing ourselves up? Again, who's the pessimist? Who's the optimist?
All right, so we'll take the final answer over here. Kind of a percentage of those that are able to actually.
100 years, 1,000 years, 10,000 years, 2,000 million.
All right, 100,000.
So with this, with just using Drake's equation, so using Drake's equation, with what we've put in here, right now, this moment, there should be 150 communicating civilizations out there. So if we think about what we've got here, so we've got our hypothesis so far. So we know we can kind of define life, right? Pretty confident.
All right, and so really, what are those conditions? And so when you begin looking at our galaxy, and we talk about that 150 possible societies, and we've only been communicating around 100 years, we're not even like connecting with one another yet, right? All right, so what's our next point here, Mike? Yeah.
This is the fact that we know there are we know there are conditions other than our own planet that could have supported life in the past. So Mars is a perfect example. So we know places could have had life.
And whatever happened on Mars, we're not sure what that is. Whatever was there was completely blown away. So, there are even more moons that could be habitable. I mean, we just talked about Titan. We talked about Enceladus. We talk about Europa. Of course, there's also Ganymede and Callisto as well. So there are possible moons, not only in our solar system, but in those exosolar systems that we discovered that could possibly harbor life.
And we know exoplanets are abundant. We found those. We know that the galaxy is old. It's 13.5 billion years old. And we also know now, thanks to basically James Webb, that apparently massive galaxies, were around, and they were around very early on in the universe.
All right, and so it really only take an advanced civilization roughly about 4 million years to colonize our entire galaxy. So where are they? Where are all the aliens? And so this is really the Fermi Paradox that we have talked about on many occasions. And this basically came from our famous astrophysicist, Enrico Fermi, who is also the father of modern nuclear reactor technology. And as he was coming home from lunch going out to lunch with a bunch of his friends at Los Alamos laboratory, he asked the question. So if there are all these opportunities for life, if there's millions, and we've discovered millions of planets, we've got, at least 150 possible civilizations. Where are they? Where is everybody? And so that's what our topic is tonight. And we're talking about possible solutions to the Fermi Paradox. So if we have all that, Anna? That's great.
We're just talking about this guy.
Yeah. And in our hypothetical galaxy, we only came up with 150 civilizations. Again, with that communication that we've been doing, we're not even touching one another. Right. So in the Fermi Paradox, we do have solutions. Why is it that possibly that we haven't been able to connect with people? One of them is that space travel is just too draining on a civilization's resources. We know for our own, it's very expensive. Of course, with that expense, we also get a great return on our investment. all our cell phones are direct results of the space program from Apollo and from other research possibilities or other research efforts. So there's a lot that we get from that, but it is draining on resources, and it's very slow, very slow. Right. You want to take the next one? All right. So space travel and colonization is basically demanding on the aliens. Their bodies may not be able to take it. You think about us. You know, we can't survive 100 years, you know, on a spaceship going towards where, you know, because we can't travel at 10, even at 10% the speed of light. So it's very demanding on the biologics that are trying to explore space. We have to find some way to kind of, you know, bridge that big divide of light speed. All right. Advanced alien civilizations may simply choose not to visit us. I mean, look, let's talk about reality here, right? We've harnessed the atom, and it's a great benefit. I mean, our nuclear reactors, nuclear batteries, all sorts of wonderful things to actually make our society great. And what do we do? Well, we just point them at one another. I mean, you know, you think about it, we weaponize the atom. And so any intelligent race would just say, hey, you know, hard left, you know, no fly zone around our solar system. So, yeah. And then, of course, advanced alien civilizations may have risen, you know, really too recently in order to reach us. And that's what we were talking about that communications gap. And the final one. Yep. And so maybe they have visited us, but, you know, but we haven't been able to connect them. Maybe they've communicated, but maybe their communication is over light. And right now, ours is really low in the electromagnetic spectrum. So we're not actually, you know, our radio and microwave, we're just crossing paths, not seeing one another. All right. And then there is this probability, this idea of great filters. Great filters could be in place that actually prevent a life from moving forward. And so
we'll talk a little bit about those. So if you think about it, this filter could be an event or any kind of condition that could actually prevent the development of advanced life. You know, again, maybe lack of you know, the right climate, lack of a number of different things. Or it could be an event that actually hastens the extinction of life. So you could have filters that we've crossed, but there might be filters that are ahead of us. So I like this diagram. It kind of looks like a big bunch of spaghetti, but each one of those lines is basically a pathway trying to get to from kind of the origin of life to becoming advanced communicating civilizations. And who knows, some of them may have passed certain filters. Other ones may have not. And, you know, there could be a huge filter that maybe lies in front of us, that it's the great filter. We still have to overcome it. So, yeah, and it might just be that most everything is filtered out and only the very, very few survive. So we're going to do a poll here and kind of ask about maybe filters that we have passed, things that we've already completed that have enabled advanced, again, still theoretical advanced here on, or intelligent life here on Earth, but great filters that we've passed.
I think you're the rover on this.
Okay, I'm the rover. Yeah, okay. So any thoughts of great filters we've passed?
The pandemic.
Good, COVID pandemic. I like that.
So there have been, I think, 6 extinction events, and so we've passed those.
Major extinction events. Food resources. Yep. Yep. So Daniel mentioned the fact that we have a magnetic field that helps keep our atmosphere from being blown away by solar winds, and it also helps keep us from being irradiated.
Life moving out of the ocean onto land.
Okay, so life definitely has to move out of the ocean, because someone's just stuck in the ocean. I mean, how do you, arguably, we evolved and we used things like fire to light our way to help, with tools and smelting. It's hard to do that underwater. Another one.
Jason on Zoom says Ice Age.
Ice ages, yes. So we've passed some ice ages. So Doug, why don't we flip through what we thought they were? So habitable zone. So we've got to be in the right place. I think that was somewhat alluded to. Plate tectonics. We've got a very large moon that has stabilized our tilt. If we didn't have that moon, we would have basically variations in the tilt where at some point you'd have Antarctica down at the south, but then 10,000, 15,000 years later, it could be at the equator, just because, again, the tilt. We've got the magnetic field, I think, as Daniel mentioned, various extinction events. We've passed them, so that's good. And those extinction events paved the way for mammals. So otherwise, we wouldn't be here, and there'd be a bunch of evolved dinosaurs having this conversation. And we need fossil fuels. So can you imagine if we didn't have any fossil fuels? If basically the most that we could ever do would be burning wood, where would we be? We wouldn't be able to have an industrialized revolution. You wouldn't, because you wouldn't have coal, you wouldn't have oil, anything like that. So, and we've harnessed the power of the atom. So those are filters that I think we've passed. So now we'll go on to great filters that are ahead of us. Yep, now we'll do. Okay, anyone? So what are things that we've got to get over, we've got to get through to kind of evolve?
I heard there was once some scientists that wanted to blow the moon out of our Earth's orbit in order to have dark skies all the time. And they say you couldn't reason with them, but could you put enough nuclear bombs on the moon to blow it away like Space 1999? I've got the whole set.
Yeah, so any filters in front of us?
Definitely the fact that we do have the power of the atom, and the various weapons are being pointed at each other. So, hopefully no one.
Yep.
Sustaining in space for a long period of time.
Excellent, excellent. Sustaining in space. Anybody else? Sustaining our own Earth, I'd say. Yeah, yeah. All right, we'll get through some of those. All really good. Climate change, whether you believe it's man-made or natural, we've got to get a handle on it. Warring tendencies, like Ann mentioned, and hoarding resources. I mean, let's just face it, unless we all kind of come to a common, good, if you will, it's going to be very hard to do things. And the universe is trying to kill us. Asteroid strikes, gamma ray bursts, black holes wandering the galaxy. Just absolutely crazy. And you might have that type 3 civilization out there, the great overseers, we'll call them. And they come around every so often, look at our solar system or whatever. And as soon as one of these plucky little, tiny civilizations start posing a possible threat in the future, they just wipe it out. Again, a thought. So I guess it's a really important question is we can't find them. We don't know. There are definitely some reasons why we can't find them. But, and I challenge you to think about this, what if we are the first advanced civilization in our entire galaxy? Think about that for a minute. We're the only ones. Yeah.
Yeah, so again, we were kind of talking about that on our own planet, we're thinking that possibly the life here has existed. Our planet has existed for about 4 billion years. Life has not despite the extinction events that we had, life was resilient. It was able to kind of evolve and continue to change. Environmental changes sometimes have held things back, but have propelled things forward. And then, of course, it's been really more or less largely interrupted really for quite some time now. So we have really kind of gotten to the point where we're looking out, we're trying to communicate out, we're trying to understand what's out there beyond us. So what if someone else is trying to do that as well?
Yeah. So, I mean, it's literally, we've been around. Life of some form has been on Earth for, I think it's 3.9 billion years is the estimate. So, and maybe we're it. So do we have an obligation to spread life? Who knows? Is that literally what the first civilization in the galaxy should be doing?
And maybe we should really think about what are the things that we need to do to alter our society to make it sustainable for all people, not just for a privileged few, but what are the things that we should do in our own society? What are the changes that we need to make as a society, as people individually, to actually preserve life on this planet so that we can be guaranteed that ability to kind of reach out to the stars?
And what happens if we destroy ourselves? Do we destroy the galaxy's first chance of having advanced life and spreading? Have we just set back the clock by 4 billion years or 3.9 billion years of life if we destroy our Earth and make it completely uninhabitable? So just some things to think about. Sorry to end in such a downer, but you know, it should be thought provoking. You know, there should be aliens there. They should be all around us. We haven't found any. We think we have some explanations, but at the end of the day, what if we are the first? And I heard it said earlier, someone has to be first.
All right. Thank you all very much. We'll take some questions. Just a second. All right, Frank, make it quick.
That grand picture I just saw of Bodie Island Lighthouse, I went down there with 5 DeWalt flashlights and lit the whole thing up completely. But if I was going to take that picture and had control of the lighthouse, I would take the star picture with the lighthouse turned off, then turn it back on, and then lay a faster exposure on top of that for a grand, glorious double exposure.
Awesome. Thanks, Frank. All right, Ann.
You may not know the answer to this question, but how ancient are the tardigrades? Were they around before the atmosphere was created, that kind of thing? Does anyone know that? No, that might be why we had that. I will have to look that up.
I think an interesting thing to think about, Ann, is that microorganisms existed first before we did. So whether it was in the form of a tardigrade or not, we all arose from that. So there's that to consider. So microorganisms are very ancient on this earth.
I have an interesting question around terminology. When you wrote, do we have an obligation to spread life? When I think about the word obligation, I think, well, that's a construct. We put meaning on that construct around obligation. Wouldn't those who have a calling feel obligated? And those who don't have a calling. So are they obligated? Like, who is the first then? And does this become a splitting of our society? It's an interesting thought.
That's a great observation and question. I don't have the answer for that. If I can say, Mike, and maybe you do. But that's a great observation. All right, we have somebody over here. Anna? All right, we have some questions from chat.
We have from Tony V. He said, any thoughts about the recent radio burst detected from the depths of the universe?
Okay, so what I understand about those radio bursts so far is there's a big question about those. The problem is that we have so much electronic noise here on the planet that a lot of those bursts are reflecting around our planet. So I don't have an answer for that right now, but as I understand it, as currently, I will say that at least when they were first discovered, they actually found out that that was actually the microwave shutting on and off in the observatory that first saw them. So basically, right now, I think that those fast, rapid bursts right now are in question, but we don't have anything that points to intelligent life, as far as I know.
One more from Zoe. Weren't tardigrades found on Venus, or was that the space experiment that you talked about earlier?
Okay, that's a great question. So that was not the experiment that I talked about earlier. That was actually on Mars. But now that you bring up one of my favorite planets, Venus, so that experiment that actually came from the Parker Solar Space Probe as it rounded Venus was they thought they saw a signature of life in the upper atmosphere, but subsequent passes actually have shown that their detection wasn't calibrated. And so that's kind of been filtered out. So, but that's a good question. But as I understand it now, they've kind of discounted that finding. One more.
Jason asks, are we actually attempting to transmit beyond our solar system? What kind of gain would be needed to escape solar emissions?
What kind of gain? Okay, that's a good question. I don't totally know the answer to that. I know that they did that with SETI. Go ahead. Mike.
Yeah. So they have sent messages out, and obviously we've sent probes out. And it's not necessarily a question of gain, because I don't think you could ever get enough gain to actually get those messages as far as you want. It's really about narrowing the field where you're broadcasting it. So you've got to kind of narrow that. If you're just kind of broadcasting everything, it's, it will fade. Yep. Okay, narrow band, it says.
I could be wrong. I think that they're over 500 million years.
So 500 million years old for the other question about how old or how yeah. Okay.
This one's not as deep, but I'm curious, you didn't discuss Oumuamua. Is that an Oumuamua? Is that complete that it is a rock?
I'll take that one. So I personally, this is my personal feeling on this, and there are others who feel this way. That's probably the first indication that we've really seen of an intelligent extraterrestrial ship, and I'm not the only one who's saying this. Okay, we have and I cannot remember the astrophysicist's name from Harvard, but it is. But the thing is, when you look at the orbital trajectory of that quote asteroid, if you're going to come into our atmosphere or into our solar system, you can't come along the orbital plane, because if you okay, so Oumuamua was an asteroid that actually entered our solar system, and it actually did a flyby of Earth, roughly in October 2020. Yeah. So and then it sped out of our system. What was interesting about that, and let me just go back to what I was talking about. When you look at the plane of our solar system is organized in such a way that objects entering along that plane are immediately shunted along the gravitational pull of Neptune, Uranus, Jupiter, Mars, and on right into the sun in a parabolic trajectory, or out in a hyperbolic trajectory. So coming along that orbital path is not a good idea for anyone trying to enter our solar system. So quite naturally, natural rocks and stuff like that do that. As they're approaching our star, they get aligned along that path. And we have virtually very few objects that are actually coming from the top, relatively few. If you look at the orbital trajectory of Oumuamua, it actually came from the top of our solar system down, aligned itself with Earth, just like we would do a flyby. And it received energy from the Earth's rotation to push it out. Now, quite frankly, it's just from a random possibility of something like that happen, I find it relatively improbable, but it could be. So I don't know, but it certainly looked like if I were going to do a flyby, and if I were going to enter a solar system, I would enter from the top where I wasn't affected by the gravitational pull of those large Jovian planets. And if I only wanted to look at the place where I thought there was life, I mean, that was the only place that went It went down to our Earth, it did a flyby, and then it went out. So that was a very interesting. And also the other thing I read about it was it's tumbling. And so if you were going to create a generational spaceship, it would be of that same ratio, the size of it, and it was tumbling, which was creating its own artificial gravity. So anyway, again, we don't know. Mike, you might have some thoughts on that, but.
Ditto.
All right, there we go.
All right. Any other questions? And check. Yep.
So the moon, how important is it for, creating life? Like Earth is the only planet, in the solar system that has a moon that's that massive, also happens to be the same size as the sun and, the sky, which is also a huge coincidence, right? Or is it?
Yeah, so in terms of the size of the moon relative to the sun from our perspective, that is right now it's a happy coincidence. The moon was much closer in earlier on, and we'll eventually lose the moon. But I think Earth will be a big ball of charcoal by then. I would say that the moon was very, very instrumental to creating life. Because of the massive tides that we had at that time. You're basically circulating a lot of that, the minerals in the water that are deep down low. So it helped build, kind of that stream. And even today, without the tides, that would severely negatively impact the entire food chain in the ocean. So yeah, me personally, it was like, without the moon, I believe we would not have evolved.
And I agree with that. There's some other really interesting facts about the moon that most of us don't think about. And as I was talking about those asteroids and those ejecta that are actually coming around, once they make it around the sun, they get to Mercury and Venus, which take their impact. And then anything that gets past that, we have this wonderful gravity well in the moon that has taken it on the chin from Earth. And all you have to do is look at the moon on any given night and see all those craters in the mare, and you realize the moon has really taken a lot of impacts for Earth. So things very rarely get through or pierce that lunar veil. The other thing too about the moon is as the moon orbits, it actually tugs on Earth's core, which keeps the friction on our core, which keeps the core spinning. And as we mentioned earlier, a spinning magnetic core creates an active magnetic field, which if you look at Mars and you look at Venus, they don't have one. They have a passive magnetic field. So that's something that the moon does for us. And finally, one other thing that the moon does for us, and Mike's alluded to it already, it really serves as a counterweight. If you look at Venus, Venus is flipped over on its side at 177 degrees, okay? So it's almost 180 degrees completely on its side. Whereas Earth, the moon actually serves as a nice counterweight, a counterbalance out here. And as really, I think it's about a 14,000 year cycle, our Earth moves between 22 degrees with respect to its axial tilt to about 25. Right now we're at about 23.4, I believe, right? So that means that we get nice warming, even warming as we orbit the sun for winter and summer in the northern hemisphere, and of course summer and winter in the southern hemisphere. So the moon does this for us. You look at Venus, Venus doesn't have that, okay? Venus is very hot. Venus is about 878 degrees Fahrenheit on average. It has molten rivers of lead and magma. So it's very hot. So it doesn't have the benefits that a moon would give it, basically from keeping it falling on its side, and also by allowing it to kind of maintain that axial tilt for a consistent warming. Go ahead, Matt. Yeah.
Carrying on that thought, how strongly were you looking for moons around some of these Earth similar exoplanets we found?
At the moment, it's pretty much beyond our capability. a lot of what we're able to find and really start to get some details on are when you have a transit and you can do the radial velocity. So that will tell us many things about that particular exoplanet. But yeah, we just do not have the resolution power to catch the planet and its moon today. So that could change in the future. And I don't know if they'll ever have Webb do some kind of exoplanet survey. I don't think, I mean, its cameras aren't big enough, don't have the sensors to do that. You can try and image one, but like what we did with, can't remember the name of the space telescope, Kepler. Whoa. Okay, we did with the Kepler program. I mean, that basically was able to stare at 100,000 stars all at the same time. And that's how big the sensors it had. So yeah, at the moment, we just can't, but it's an engineering issue now. It's not that we won't be able to do it. All right, so we will close here. Thank you very much for the questions.
Awesome. Thank you, Mike. Thank you, Doug.